Oh, sorry. I forgot my microphone. So, okay. So here are the heads up part. So for each class, we'll do a recap to recap the critical contents from last week. So first of all, like last week, we first talked about the computer organization. So there are compute memory and I/O. So I think the most important thing is how CPU works to access the process. So actually, when people are saying about process, it's about a combination of the program and the related CPU and memory resource, right? So for a program, just like you write a C code and then you will put a C code on the memory. So actually the C code will be first, will be compiled and then to go through the assembler, and then you'll get a lot of instruction there. So actually C codes on the memory, that looks like a sequence of instructions. So CPU reads the first instruction and then do the decoding and execution. So after that, CPU will fetch another instruction. So CPU does this by automatically increment the program counter. Okay, so there is nothing special here. It's just about to increase the program counter by, for example, by 4, like 32 bits, and then the program counter will jump to the next kind of address. So CPU can fetch another one. So CPU only does the routine works. What I mean with routine works is if there is no like branch condition, like if else, if there is no jumper, like the go to instruction, the CPU will fetch the next instruction and then the next one, okay? So the next thing to recap is about the Linux kernel part. So Linux kernel is a process manager, consists of a bunch of C and assembly code. And people are usually curious about, like, is Linux kernel a process? I would say no, not that exactly a process. The reason is when we are talking about a user process, like these kind of things, they should have their user address space. Okay. So let's we talk about like the virtual address space part. So we will not go through it today. So kernel runs as part of a user process. So you can see at the right-hand side, usually for each user process, they have their own address space. So including the user part and then the kernel part. Okay, so you can see actually the kernel part is designed for running a kernel process. Okay, so for each user process, when they run the process, actually the lower, for example, 3 GB, they are all allocated for user program. So you can put your user program here, and then you can put your, like, the process can put their process data here. Okay, but for every process, they will leave their top, for example, 1 GB address space for the kernel. So this is the reason I say Linux kernel is not like a process, because they only have their kernel address space. Kernel doesn't have their user address space. Okay, so the reasons, like, each user process has their corresponding kernel part. It is because we say in CPU there is a bit, but actually it's not really only 1 bit, because if you read the OS if you read the OS textbook, they will say there are 7 modes there, or like there are 5 modes there. But I think the most important thing is actually in CPU, there are 2 different modes. One is user mode and the other is kernel mode. So when CPU is in the user mode, CPU can access user process, user program, process data, but CPU will not access the kernel part. Okay, so for example, when there is a patch fault, this kind of things, what I mean patch fault here is when CPU needs to run some OS kernel service. In this case, CPU will switch their mode from user mode to kernel mode. Okay, so switching this mode only involves to switch the bit, for example, from 0 to 1. So it is super fast. So after switching the bit, CPU can access the data or like a function in the kernel address space on the topmost here. Okay, so for example, if this is a patch fault, actually there is a corresponding patch fault handler. So you can think about patch fault handler is just like a function call Okay, just like a function, it is named by the page flow handler, and a function is like here. So CPU will start to run the page flow handler one by one, okay, by its instruction. So this is how kernel works. So the important thing is CPU switch to kernel mode to access OS code, but CPU does not need to switch the context. Okay, so the context here we usually means the user process context. What do I mean CPU doesn't switch the user process is actually CPU only switch to kernel mode and to access the other part of address, but the user address space here, it doesn't change to any other, right? The address space is still the same, stick with the original user process. Okay. So we also use like a toy example, submarine, to let you know what the concept is telling us. Actually, you can think about a submarine is just like CPU running like process A, like here. So when CPU is running user process A, it is in and the submarine will be on the surface of the water. It means CPU is now in a user mode and running process A. Okay. So when CPU needs to run some OS kernel service, the submarine will dive into the water under the surface. So it means like CPU enters the kernel mode. And in this mode, CPU can run some kernel service. So like file system, scheduler, memory manager, all those kind of things. And the key point is actually for the user address part, this CPU still holds process A. So process A doesn't need to be switched out to other like kernel process. Okay, so this is a key point. We don't really switch the process. We only change the CPU mode. We only change the CPU bits. Okay. So here is a more details about how to trigger and request kernel service. So when do CPUs run kernel? Actually, CPU runs a kernel only when some spatial events are triggers. So here are several spatial events. We classify into the hardware events and software events. So for the hardware events, they're like timer interrupts. So for timer interrupts, you can think about usually for each process, they only have a given time slot. So after running out the given time slot, CPU will raise a timer interrupt to say, hey, it is time for you to switch to other process. Okay, because you use too much of time, so you need to let others to run. So this is about timer interrupt. So IO interrupt is quite simple, just like the keyboard and hard disk drive, this kind of peripheral device, when they are going to send the data to CPU, then there is a interrupt occurs. And software generated interrupts usually like traps or exceptions. So you can think about things like system call and like patch flow, those kind of things. They are software generated. Okay. So the same example here, just like here is a user process, and when the submarine is above the water surface, it means the CPU is in the user mode, and when the submarine dives into the water, it means CPU is in the kernel mode. So we use the same example. So when there comes the system call, for example, when you write a program like you are going to read a file or you are going to write a file, then after the library translate, it means CPU needs to do some system call to interact with the hardware device, right? Because when you are saying you are going to read a file and write a file, it means you are going to read something from hardware device. Okay, so usually when there involve some other hardware device, it needs system call. So system call handler, it is a part of the OS service. So CPU needs to enter the kernel mode to run the system call handler. So after finishing system call handler, CPU will switch back to user mode to keep running process A. Okay. And then if process A use up the time slot, for example, it runs too much of time, then CPU will trigger the timer interrupt. So after trigger timer interrupt, CPU will switch to the kernel mode and execute the CPU scheduler. Okay, so CPU scheduler is another kernel service, so CPU should be in the kernel mode to execute it. Okay, so After running the CPU scheduler, usually we will switch on the prior process and then we will run another process. For example, it's process B here. So we change the icon to another submarine to represent, hey, this CPU is going to run another user process. So we call it process B now. Okay. So after running process B, after running the scheduler and then the CPU switch back to user mode, you can see like now process A changed to process B. So CPU now is running process B. So we call this procedure called the context switch. Okay. So from process A to process B, it is context switch. Okay. And then if there comes an IO interrupt, for example, then process B will once again dive into the kernel mode and then CPU can run IO handler. So this is the process about how to trigger and request kernel service. I mean, you guys, if you don't feel like really familiar with this kind of procedure, it doesn't really matter because in the rest of the course, you'll keep facing this kind of example. I'll let you know like there are several kernel service and how it works in the kernel mode. Okay. So let's start for our main course. It's about what is a process. So last time actually we slightly talk about some briefly idea about the process. So today we'll also do the quick recap about what we talked about last week. So first of all, process just like an active program and related resource. So there are several related resources. For example, the processor state, the memory state, the file state, network state. So most of the power resource that this process is required, we will call them the related resource. Okay. Okay. So because there are so many resources and different resources will have different state, so we need a data structure. We need a kind of a metadata to keep track of those resources. So for each data structure, we call them process descriptor. Okay. So because there are several processes in the system, so there will have several process descriptors. And there is a data structure called task list. Task list is going to chain all the process descriptors together. Okay. So just like the figure on the right-hand side. Okay. So what is process descriptor? So in Linux, process descriptor is just like a function. So just like the tag stack structure. So this is a name for the process descriptor in Linux. So it contains all information about this process. So each process has their own process descriptor. So you can take a look at this figure here. So for each tag structure inside, there are several fields. So one I think you'll be very familiar with is the process ID. So because of each process shall have their own process ID. So process ID is one of the field breaker in the text structure. So, we already talked about this. Just like in Linux, like there are a lot of descriptors. It just means the data structure for maintaining information. Okay. And then in your undergraduate, maybe you still remember there's one word called process control block, right? So process control block or PCB in Linux called it the process descriptor. So they are the same things. So process control block, it is a concept, and process descriptor in Linux, it means the implementation for the process control block. Okay. All right. So there's a quick question: is the difference between process and program? So usually when we say program is when you're writing a C program, when you're writing a C++ program, it's like when you open a kind of a text editor and you put several code on it, and this is called a program. So process, it is a runnable program. So it means process includes some resource, because if you are going to run a program, actually you need CPU, right? And you need memory because you need to put a program on the memory. So when Linux is going to keep track of this kind of information, then those kind of resources are needed. So for process, it means the active program and the related resource. Okay. Okay. So we also talk about state field. So state means like what is the state of the current process? So actually there are quite a lot. There are 5 states. First of all is the task running. So running means it is runnable. Okay. So runnable means the process is now running, or the process is in the run queue, or usually people call them ready queue. So there is two possibilities when the process is in a task running state. It is running now or it is in the ready queue. Okay. And there's two stat for interrupts. So there is a stat called task-interruptible and task-uninterruptible. So interruptible stat means the process is now sleeping, waiting for some conditions. For example, the process is waiting for the I/O completion, because maybe the process needs the data from a storage device, right? But storage device is so slow, so CPU doesn't want to wait for that storage response. So the process should be forced to sleep. So in this case, the state of that process will be marked as the task interruptible. Okay. And there is another very special thing, it's called task uninterruptible. So it is also the same. The process is not sleeping now, but it will not wake up by the conditions. What I mean is, actually, it can only be wake up by some special kernel thread. Okay, so usually it is used for the fork process. So when we are going to create a new process, at that time, the new process will be set to the task uninterruptible. Okay, only some kernel thread can wake up this new process. We'll explain this later. So there is also some very kind of spatial stat here, but last time we talked about it, so let's skip it now. So, because there is a stat, so usually in your textbook, you will see there is a thing called process state diagram. So process state diagram is just like a life cycle for each process. Okay, so let's look at the left-hand side. It is a concept, and the right-hand side, it is the implementation of Linux. So when the process is new, means that the process is just created. In this case, people are saying like we use a fork kind of system code to create a new process. And later on, we will talk about how fork function works like. So after creating the process, actually, the process will be added to the ready queue, or like to add to the run queue. So at this moment, the state of the process will be changed to the task-running. Okay, so in the ready queue doesn't mean the process is not running. It just means the process is runnable. The process still needs to wait for a CPU, right? Because maybe there are a ton of processes that are in the ready queue, but there are very few CPUs that are available. So the next thing is, if there is a kind of a CPU and it is possible to run the process, and the process will be scheduled and then to be running. So you can see like the ready queue, the process will be picked from the ready queue and then to be run. In this case, the state will not change because it is still the running state. Okay, so both states, there are still task running. Okay, so there is a case is, for example, if the process is interrupted by some other process. For example, there are some other process that have higher priority. Then the process will be put back to the ready queue again. Okay, like this, interrupt, put back to the queue. So I think it's here. So if there is a higher priority process, then the process will be put back and the high priority process will be run now. Okay, so in the running step, when the process is running by CPU, there are several cases here. So one case is we finish running the process. So it is called terminated. So when the terminated, it means like the CPU should terminate the process and CPU will release all of the resource allocated to that process. So it is the termination state. And we will talk about how to terminate a process later. So there is another is the I/O or event wait. So one very obvious example is when this process now needs some data from a storage device. And then in this case, CPU will switch the process to the waiting queue. So in the waiting queue, it means like this process is now waiting for the I/O response, waiting for the I/O completion, right? Because the process is waiting for the data in the storage device. Okay. So in this case, you can take a look at this circle. Actually, there are two possible states. One is interruptible and the other is uninterruptible. So it just depends. In most cases, it will be set to the interruptible. It means after the IO completion, the state will be switched back to the task interrupt. Sorry, the task running. Okay. Oh, there's an animation here. So those are like we talked about last week. So this week, let's start from the process creation. So usually, already know process creation in most of the operating system, we use fork plus execution, right? So fork means we create a child by copying its parents. So it is quite simple. And the design concept behind this fork design is because it is efficient enough. Because when we are going to create a new process, if there is the parent process, we can just directly copy it, and then we can make sure most of things will be correct, right? Because the parent process is not running now. So if we can directly copy most of the resource from the parent process, then we can also make sure the child process, most of the state will be in the correct state. Okay. So there are some fields that will be different. For example, the process ID. So because process ID, each process should have their own process ID. So PID will be different. And like for each process, they have their own patch table. So the patch table will also be different. Okay. And also there are some signals that will be different. Okay. So other than that, most of things, they are same with the parent process. Okay. So the next step is execution. So execution, EXEC, is quite simple. It's just to load a new executable into the address space and run it. So executable, you can think about just like the program after compiling, there is a .exe file, right? So that is an executable. So like the binary, you can run a binary. So the binary is also a kind of executable. Okay. So address space now you can think about just like the memory, just like you put the binary on the memory and system can run them. So executable is just to put the binary file on the memory and just run it. So we will not focus too much on the execute. Let's talk about a little bit more about fork, because there is one issue here. If we are going to copy most of the, I would say like most of the stats data from the parents, it may take a lot of time, right? For example, if this parent process already has a really large memory, for example, 1 GB memory, and if we are going to copy it, it will take a lot of time, right? So in this case, there is a design called copy on write. So copy on write is going to solve the challenge. Just like naively copying all resources from parent is time consuming. So we don't really copy at the time the parent does the fork function. Okay. Then how can the system do the copy? So copy on write works on delaying and preventing copying data until the data is written. So you can think about if most of the data is read-only, then we don't really need to copy the data, right? Because if the data, we only want to read the data, then you copy all data, but they are the same. In this case, why not just share the data, right? So we only copy the data, they are updated. It becomes a new one, okay? So the system will only copy, for example, if the child process is going to update a patch table, is going to write a new data, or if the child process is going to store a new file, because they are new, so we need to write them to a new place. So at that time, we do the real copy function, okay? Unless if the child process only read the data, only read the patch table, and we don't really do the copy, okay? So let me give you a quick example here. So come to think about so let's image like here, the rectangle box here is a physical address. It's just like a DRAM, okay? So we say like we put the binary on a DRAM, right? And on the DRAM, there are several things. the first thing is the patch table. So I think it is quite hard for some if you did not take the undergraduate. So I try to use some example to make you easy to follow it. So you can think about like the virtual address, just like the mail address. Okay, so each house have their own mail address, right? But the mail address is not the mail address is just about, for example, in this country, your mail address is that. But for other country, they don't really understand what is a mail address, right? So there is a more absolute way is the physical address. So physical address just like the latitude and longitude. So you can think about the Chinese for this is like 经纬度, okay? So using this longitude and latitude, you can get the absolute address, okay? And the thing is how to translate the absolute address to the mail address. Then that is called a patch table, okay? So just like if there's a patch table to do the translate from the mail address to the latitude and longitude, then you can people can easily know where is the for example the house. Okay, so after introducing an address, there's another thing is patch, because we talk about a lot about patch from the very first class. So for patching, you can think about we are going to evenly partition the land, right? For example, if you can think about if there's a country and there is a super large land, then we are going to construct several houses on it. And in this case, how to do the partition? So for the Linux, actually, we will evenly partition the land into the same size. Okay, so you can think about for each 4 kilobyte, we will do a patch here. So just like, for example, you have a super huge land, then you will partition the land into the same size. And that size is called patch size. Okay, so you can think about like this. You can construct a house on the evenly partitioned land. So for example, for each kind of 100 kind of meter square for this kind of things, you will construct a house, and for the next 100 meter square, you will have another house on it. Okay, so each house has their own mail address. That is called each house has their own virtual address, and then also has their physical address, just like using the latitude and longitude. So they are very similar for Linux here. Okay, so in Linux, the LAN is just like the physical memory here. Okay, so for the physical memory, we will partition into the same equal size, the 4 kilobyte patch on it. And for each patch, you can store the data on it. Okay, so patch table is a way to translate from virtual address to physical address. So actually, patch table is also a kind of data. So patch table will also on this LAN, okay, on this physical address. Okay. So, okay. So the thing is like this. So when CPU is going to access the data, for example, it's going to access this patch frame, but CPU doesn't really know where the patch frame is, right? Because CPU only, for example, in this example, CPU only has their mail address, but CPU cannot really understand what is the absolute address is. So CPU will first check the patch table. So inside the patch table for each entry, there is a mapping between the virtual address and physical address. Okay, so in current CPU, actually CPU will only get a virtual address. So CPU will ask about where is the physical address. So after CPU getting a physical address, CPU can, in the second step, can directly access the patch located on this physical address. Okay, so this is about like how CPU access the data on it. Then now, if, for example, if process 1 is going to fork another process, so let's say process 2. So actually, after forking a process, at the moment CPU, process 1 forks process 2, the patch table will not be copied. Okay, so patch 1 and patch 2 at the very first moment, they will only share the same patch table. So when patch 2 is going to update the patch table, then the patch table related to patch 1 will be copied and then to modify to patch 2. Okay, so you can think about at the very moment they are all read only, and when patch 2 is going to write a patch, for example, patch 2 is going to write this patch, then the patch frame will be copied out to the new patch frame. And then the patch table will be updated to point to the new location. Okay, so this is the concept of copy on write. So the good thing is actually process 2 only need to copy out the patch that they are updated. So the rest of it, for example, for this patch, they are still in the share state. So process 1 and process 2, they still share this patch frame because this patch frame is still not updated by process 2. Okay, so in this case, the process can be forked super fast because in most of the data at the very beginning, they will not be updated. So we'll only do the copy when the data is updated. Okay, so this is just a very kind of tiny example to show you how copy on write works on the patch like perspective. Okay, yep.
We have so if we have 2 forks from E1,
Mhm.
we have 2 and 3,
Mhm.
and they are read only, and then write to like E1's page table.
Mhm.
Will 2 and 3 both get their own page frame, or will they be able to share one?
Actually, if there's 2 forks, and then for example, process 2 is going to modify the patch table, then process 2 will get a new patch frame, a new patch table. But for process 3, they will still share with process 1.
It's the parent that changes?
If the parent changes, then the parents will get another new patch out.
Okay, children can still share.
Yep, yep.
对到对对都是一样的，
嗯
所以直到它有写入或是的要求。
Yep. Yep, correct. Yep. All right, so any questions? Okay, so if there's no question, then let's move on. So this is the roughly concept about the copy on write. So how Linux implement? So Linux actually there is a new function called copy process. Okay, so for copy process, let's talk a little bit more about copy process. So actually, when we are going to create a new process, there are several things that we need to do. First of all is to allocate, sorry, where's my mouse? Okay, so to allocate a new kernel stack, and then process descriptor. So I think I didn't really talk too much about kernel stack last week. We only say, hey, actually there's a thread info. So you can think about like this. When you are going to run a user process, right? And maybe there are some function code. So when you are running a function code and there are some parameters, right? So those parameters, they're usually stored in the user stack, right? So kernel is the same things because when you are running a kernel, like when you are running some operating system functions, there are also the functions. So inside the functions, for example, maybe there are some parameters. So for those parameters, they need a place to store them. So they are all stored in the kernel stack. Okay. So to maintain those information, we need the data structure. So this is called the thread-info. I mean, this is a very simple way to explain it, but actually in a complex way, they are super complex. So let me just skip the kernel stack here. Okay. And another thing is the process descriptor. So because each process have their own process descriptor, so in the very beginning, Linux will allocate a process descriptor for the other process, like the child process. Okay. Okay, so inside the process descriptor, actually there are several fields, right? So there are something that they can be set and they can be copied. So for example, the program counter and the stats, they will all inherit from their parents. And then for the process ID, actually they will be set to the new process ID here. So this is about the process descriptor part, just like the text structure. Or you can think about it's an identification for each process. Okay, so this is the second thing. So third thing here is the stat that we just talked about, the task uninterruptible. So each new process at the very beginning, they will be set to the task uninterruptible. And this is because the process now is still in the initialization state. So we don't want any kind of accident occurs here. So only the kernel thread can wake up this process. Okay, so this is non-interruptible for most of the signals. Okay. Okay, so then we will duplicate parents patch table via copy on write. So the thing is, actually, including a patch table and patch frame, they are shared between the parents and their child. So they will only copy out new patch table and then to copy out new patch frame only when there's some data is updated. So I say like they are copy on right here. Okay. So otherwise, if we follow the original rule, actually we do the fork. Actually, if the process has a lot of patch frame, then we will do a lot of copy process here, and then it will be wasted and will be time consuming. Okay. So actually, there is one very interesting thing is, I think you guys know about there's process and thread, right? So actually, the difference between process and thread in Linux is about how many resources they are shared. Okay, so the thing is in the process, most of the where's my mouse? Okay, for the process, most of the resource, most of the kind of files, file system information, signal handler, address space here, most of things you will finally be duplicated, right? I mean, if there's an update, then we will do the copy on write for the process. So eventually, most of the resource, they will be duplicated out and they will become a new one for a new process. Okay, but not for thread, because thread, usually they share most of the information. For example, open files, files in information, signal handlers, and process address space, they are shared between each other. Okay, so this is a difference between process and thread. And there's more details at the next page. So actually, people are saying like thread is just like a lightweight process, and it executes within the same program in a shared memory address space. Okay, so usually when we talk about threads, we are saying like they share open files and patch tables. So the thing is, for each thread, usually they will share a patch table with the process create those threads. Okay, so they will not have their own patch table. So for patch table, actually is each process has their own patch table, but not for thread, because thread share the patch table with their, I would say like with their parent process. Okay. So this is the reason why Linux implements all threads as the standard process. So in Linux, people are saying like, what is a process? Actually, if they have their own text structure, people are saying that that is a process. So for threads, they doesn't have their own text structure. They're shared between each other. Okay. So threads have their own program counter, because program counter means when we are going to run the original code, then we need a program counter to know where is the next kind of instruction. For example, we're going to increment the program counter, right? And then threads have their own register, because they're going to run as like a process, but not really a process. And also a stack, because when you are writing a thread, for example, pthread, this kind of library, when you are writing, actually you are possible to write some function there, and there's parameters. So for each thread, they need their stack to maintain their own like function and parameters here. Okay, and also threads have their own stat. Okay. So in Linux, it doesn't really provide any spatial scheduling or data structure to represent threads. So the only difference between thread and process is just about how many information they are shared between each other. So if they share a lot, then probably that is a thread. So if most of the informations, most of the resource, they have their own one, then that will be process. Okay, so even during the scheduling, there are same things. So that looks the same in Linux. Okay. So creating a thread in Linux, actually there is a function called clone function. So clone is identical to fork. So except the address space, file system resource, file descriptor, and signal handlers, they are shared between each thread. I mean, created by the same process. Okay, so you can see like for the clone, you can customize what kind of information you are going to share. So like virtual memory, file system, files, and then signal. So they are shared between threads. Okay, so when we are talking about thread, actually there is a very important thing is called kernel thread. So usually kernel thread, it likes the daemon or like a monitor. So kernel thread will monitor the system kind of utilization usually. So kernel thread runs kernel tasks in the background. So because it is a kernel task, so kernel threads do not have an user address space. Okay, so kernel thread only have their own kernel space, kernel address space. But just like normal process, kernel thread, they are schedulable and preemptible. So they're just scheduler. They can be scheduled just like the normal process, and also they can be preempted by other kernel threads, for example. Okay. And the thing is, kernel thread different from the user thread is it operates only in the kernel space. So kernel space means CPU needs to switch to the kernel mode to execute it. So when the CPU is in the user mode, CPU cannot run the kernel thread. So actually, because it doesn't have their own user address space, so when kernel thread is going to do the context switch to another kernel thread, you'll be faster, okay, because it doesn't have their own user address part, okay. So this is about process and thread, okay. So after talking about a lot about the process, the final thing is, so how to terminate a process? I mean, there's one day a process calls the exit function. So the process is going to terminate itself. So termination occurs when the process or C compiler calls the exit. Okay. So there are several things we need to do for this process termination. The first is to set the pf-exiting flag. So this is just like the process flag -exiting. It is a flag in the text structure. Okay, you can find this flag in the text structure, and if it is set, it means this process is going to be terminated. And there are several things that the system needs to do. The first thing is to exit the MM. So MM makes the memory management to release the memory address space. So the second is to release the semaphore, because for each process, maybe they will hold a lot of semaphores, and we are going to release those semaphores so all the process will not be blocked. Because when the process is dead, for example, it terminates, and if it doesn't release their semaphore, then maybe it becomes a deadlock there. So the other process cannot use the resource. So the third one is a file. And file is quite special here. Actually, it only decrement the usage count of object related to the file descriptor. So because there's some cases is the file will be shared between a lot of process. So we only decrement the usage count. So if one day usage count becomes 0, then we will remove the link here, okay? So the next thing is they will call an exit notify to send a signal to the text parents to reparent any of the text children to another thread in their thread group or the initial process. Okay, so if the process is going to terminate, and if there are still several children here, then Linux will do the reparent. I mean, we will get the elder kind of process and then to do the reparent. So if there is no elder process, probably we will reparent to the initial process here. So they just kind of the routine things that it needs to do. And then the last one is to do the schedule. So to switch to a new process because the process now is terminated. So the next step is to schedule to run another process. So after the parent retrieves the information, the process kernel stack will be deallocated. Okay, so the kernel stacks, inside the kernel stack, there's several things like thread info and text structure, those kind of things, they're all in the kernel stack. and they will be deallocated. So it means after this step, the process is not alive. Okay. Okay, so next thing we are going to talk about the scheduling thing. Okay, so first of all, let's have a few kind of naming things. So first of all, if we have a single processor, so single processor here, you can think about just like the single core. Okay, so usually people use time sharing to share the single core, like because there's one core only. So if there are several processes they are running, then they need to share this like single core. The reason I didn't say single processor is just like a single CPU is current CPU has a lot of cores. So this is the reason I say single core. Okay, so for a single core, just like if we are going to share this core, for example, for each process, they can get, for example, 1 second to run this core, to use this core. And people are usually calling this is called virtual parallelism. So it's just about each process thinks they are running in a parallel way, right? But actually, they are not really running in a parallel way. They're just using the same CPU. Okay, so you can think about the reason is when the first process is running on is first using the CPU core, then the rest of them they are in a sleep mode. So when the process in a sleep mode, they will feel like they are not running. Okay, so when it switches to the second process, then the first process will again becomes to the sleep mode. So the first process will feel like, hey, it always run when it is awake. Okay. So there is another thing is called multiple processors. So just like there are several cores there. So for multiple processors, it is a true parallelism. So at the same time, it is possible to run, for example, 2 process or like more process. Okay, so the criteria for schedulers, actually there are several criteria here. Just like you want to make your scheduler become so fair, or like you want to have more interactiveness, just like you want to make it have smaller response time to faster response time, or like you want to have a higher throughput. For example, you can serve for a lot of more process here. So there are different kind of criteria, and each scheduler, when they are going to design their own policy, they will make the trade-off between all these kind of criteria. So there is one category of the scheduler called cooperative. So cooperative scheduler means process will voluntarily yield the CPU. It means like each process they will yield their CPU in a voluntary way. Okay, but this is not what Linux is using. I'm just to let you know there is one category of the scheduler like this. So in most cases, in Linux, we're using a preemptive one. Okay, so preemptive means even a process doesn't want to yield, doesn't want to release the CPU, but there is a way to stop the process, to switch to another process. So you can see there is a word called involuntarily suspend. Okay, so it just means like there is a way for other processes to preempt the other process. So this is what Linux is based on now. So here's just a quick example. So when a process is scheduled and running, it is in this time slot, and then if there is a preemption and it is here, so between the preemption and the process starts to run, we call it time slice. So time slice is the time a process runs before it is preempted. Okay, so we have this time slice because we don't want to, because we want to prevent some process monopolizing processors. It means we don't want some process to occupy the processor for too much of time. We want them to become, each process have a chance to run, to use this CPU, okay? So for the scheduler, actually there are several criteria here, just like how to decide a time slice and which process should be run next. Okay, so let's take a pen and then coming back, we'll introduce those kind of things. Okay. 这个那个助教的现象。
所以说这边 process creation 是 copy and write。假设说 P1 它有10个 page frame 嘛，对不对？然后 P2 一开始先 share 这个10个，
对，
然后如果 P1 改 P2 的其中一个要写入嘛，对不对？那他只要改那个 page frame，
就是他只要改那个被写入的 page frame，
他就不用10个全部都复制掉。
不用。那因为其他还是 share，而且其他也没有改过，所以就不用。对，
所以是那如果是变成 P1 写入的话，那 P2 也要改。
就是你可以想想，那个 frame 就是 share 给2个 process， 就没有主从关系。
没有存在。
所以写入的话，那就是 P1 会在另外复制出来，然后就写到那个新的 page frame 去。那 P2 就还是用P1 之前的那个。对。
那这也要讲说 Linux 它没有提供 spatial schedule 或者其他 struct，意思是说所以它没有那种 schedule 的一些方式嘛，或者
没有，意思是说在 Linux 里面，它其实不去分，就是 process 的 thread。它排程的时候就一起排，一起排就是你可以想象的，它就是它也是个 PID， 它有个 PID， 然后看谁去拿到的 CPU， 它不会特别因为它是对，然后去设计一套为了对的排程这样子。
所以它排程
就是你可以想象成在 Linux 来讲，它不会去分你是 process 的对，但是因为我们要就是作为系统的那种课要让大家可以理解，所以才会去分说，这是 process， 这是对。就对 Linux 来讲，它只有差别是。它到底拥有的资源是比较多还是比较少？
所以是资源多就是 process 少是 thread，
就是对啊，所以就是大部分资源都跟别人共用。对，
因为我记得不是说一个 thread 是 process， 它组成是好几个 thread 组成的
，process 是好几个队组成的，所以
就是一个 process 是等于一个到多个的 thread 组合起来，还是说不同的事？
感觉应该不同东西吧？
所以
它应该只是说一个 process 可以 forward 出非常多的 thread， 然后这些 thread 都是跟这个 process 去做 share 资源上的共享。
对，
但是每一个 thread 它都会有自己的 ID， 对。但至于大部分的资源，它就是更共享的。
共享，所以 process 是单纯只有资源共享，
就是对，大部分都资源共享。
我要问的是，就是 Fred， 你说他会共享那个 files 跟 page table。
对。
那假设因为我没有学过大学部，但是我有一些概念上就是假设，如果今天是一个平层，piece thread 下去，那我有一个 program， 那如果在里面的 thread 开了不同的 file， 那它是要怎么样被 share 到，或是他为什么要做 share 这件事情？
你的意思是说，如果我一个队开了一个 file 之后，那其他
的 thread 也会可以 access 到这个 file descriptor， 就是同样的这个 files 的资讯，就是它的那个 page table。
对，
因为它每频道都同样的，
他会到就是他会看到就是那个 file 的 ID 被打开，然后是可以碰它。对。
但为什么要这样做？就是
快，因为如果每个人都要再去打开自己的话，但其实对的概念在原本就像你写 P 对一样，它其实是组程式里面会呼叫一个类似 pragma 那边去宣告说，我这边要写一个 P 对这样子。所以它是从组程式出来想要算是更好的去使用到 CPU 资源。但是它并不是一个完整独立的程式，因为通常我们在写 P 对的时候，只有一部分是可平行化的。对。那以这个角度来看的话，如果我现在这群队是要对这个档案去做平行处理的话，那如果我每个队都要去开一次这个档案的话，它所需要花的时间就会比较多。之前是为了要去做很好的 security， 就是要去做 isolation， 把所有的 process 都去独立出来，说这是 process， 所以它需要有更多的保护机制去避免它存取到别人的 file 之类的。可通常对的用意是去relax 掉这些安全性的问题，因为毕竟对就是你程式是自己写出来的，所以你希望他们是可以有更快、更有效去使用这些资源。
我问一个就是比较硬题的，这个 page table 是就是存在 MU 里面吗？还是不是 TL？
应该这样说，就是 MMU 负责的是查找这块， payload 是存在机体上面主要。
所以 MU 会另外在
就是后面其实有讲到，就是之后的 memory 那边有讲到，MU 它其实是有点像是说，它会去查找机体的哪个地方是 payload，然后因为 payload 其实有很多张，所以它会从一个 edge 连到另外一个 edge 去做存取。对，然后 TOB 它存的只是，因为你不是有一个 virtual address，你要转做 physical 吗？那一般正常 Intel 的 CPU 来讲，你至少要查到4次才要帮它查到完。那每次都大概是一个机体顺序。所以如果我今天可以直接告诉你答案说啊，你这个 virtual address 对那个 physical address 的话，就结束了。所以 TOB 在做那些事情。
它这个 cache，然后所以 MU 像你刚刚的这个理论上会查找是，
对，所以我这边写 sport level，所以它其实会有至少4张，但实际上还有非常多张。
这个之后就会提到。
对啊，对，谢谢。
我只想问一下，就是它这个 CPU 去存它的那个 virtual address，它不是存到这里嘛？然后它是说重新写入，如果需要有更改，它就会 copy on write 这样。
对。
那为什么这个也要附自己的？
因为 copy on write 的时候，只有新的 process 会有这个新的 page frame。但是旧的 process page frame 并没有这个对应关系。就你可以想象成它同一个 virtual address，但是旧的 process 它其实对应到这个人，新的 process 它应该要对应到这个人。所以他要去改他的那个 page table。对，
所以会有2个，就是这个跟这个，这个跟这个都是同时存在。只是说这个是 P2 才看得到，P1 就是这个而已。原本来讲 P1、P2 都只看到这一块，只是现在你现在分割出来，所以还有2块。好，那好，我想再问一下这个 XEM 是什么？
就是 semaphore， 就是那种有点像是，因为你可能你在写程式的时候，你可能要避免程式去抢占同样的，例如我们讲 perimeter。假设你可能大家有共用同样的资源的话，那你就会设一个类似 semaphore 去把它挡掉，说，这个资源我先使用这样子。对，
好，谢谢。
这边上次那个上的时候，这边是在讲的东西，为什么要讲？
这个其实只是想让大家知道说，因为一定会有人说，我其实有听过 kernel 对这种感觉。那 kernel 对的意思，其实像刚才提到的那样子，它大部分的时候是一个 monitor 作用。对，就是我们一般来讲，我们说这种 scheduler 的一些都跟这个是2个。对，我觉得应该像是说 kernel 它很复杂，所以它有大部分我们学到这些 OS 里面的都是偏这种的，但是它总是会有一些例外。那这些例外就是
就是讨论virtual address，然后把上面那一块割下来给。
对，
有点像记忆体，它不是会割一块给。
对，
其实就是那个意思。
对，就是所有的 OS 大部分的所有的 function， 就是那些什么 schedule 的 function 都是放在这一块所对应到的基体位置。对，所以一般来讲它是纯这样，只是说这边总会有一些，就是它为了 kernel 自己要去观察 CPU 用量如何。
然后这种也算是一个 process， 我觉得单纯做。
但它只有上面那块。对，但它没有下面那块。
还有，又想问他那个串，它不是串钱，所以它等于是就是所有的那个这是什么？distributor 是吧？反正就是全部串成一条，就像那个树的。
对，
因为最上面都是 INT， 是吧？
你可以想象就是 INT 在最前面，然后后面就是串一堆 process 这样下去。
然后就是它不会是一条线，它有可能是不同的这样。
我觉得它会不会是一条线？这个感觉要看它怎么去实说的。就因为这个只是抽象的跟大家说，一般来讲它是一个0类，所以它是可以这样去存取前后。可是它也可以做成树状的。
所以就假如我进入kernel后，就可以去这边弄人家的。
对，因为进到kernel后，就代表你已经是用那种上帝视角所以你底下的那些 process 本来就是你都可以碰到的。对，谢。
教授，想问这个，它的 kernel stack 说它可以存 task thread info，是指说，应该说一个假设，一个 process 假设叫E之后，它有分2个部分，一个是 user， 一个是 kernel，所以它自己的 thread info 就会存在，应该说这个 kernel 会开一个 kernel stack 的位置给它，之后把它存在最底层这样子吗？
对，
那这样子是每一个 process 都只会存一个自己的 thread info 而已，对不对？
每个 process 对，每个 process 就是你可以想成，应该这样说，就是kernel stack 这件事情是当 kernel 这个 user project 变成 kernel 的时候， 它需要去跑一些资讯。
对，
那在跑的时候，它不会用 user stack，
对，
所以它需要有地方来存，
对
那地方是 kernel stack。
对，
只是呢，因为这些 kernel stack 我在做存取的时候，它需要一些资讯，
对，
所以我要比较快去存取这些资讯，就是靠这个对应 port 去做
OK
对应，有点像是那种快取里面还得那种感觉。
OK OK，
对。
那我想问那个，
或许你问到这个，我可以补充一个，就是在 Linux 4.多版本之后，它其实就不是这样实做了。它这个实作是比较久以前的版本。那新的版本，因为它现在系统变复杂，所以它其实基本上它会把它对应 info 把它拉出来，所以它就不会在 button，它就可以，但是概念是一样，只是它不是真的存在 button。存在 button 的好处是，我要做存取，我只需要记这个位置，然后来这边就会直接存取。
对，
但如果不要存在 button，就是它需要有个就是记录方法，跟大家说，哎，这个可能要怎么去对应到这个对 info。对。
所以它就不会变成每个人自己都会存一个，
每个人还是自己会有一个，它存在哪就不固定。
哦，OK，那也一样是在 kernel space 里面的，就是它有，
可能一样是在 kernel 对应到那个记忆体里面。对
OK，好，
对，
那，等一下，我想一下，那这样是不是，应该说我们说就是说它会分两块，一个是 kernel 的，一个是 user 的，就是这是敌人嘛，说敌人的 kernel 都会 map 到同一块，那这样子它要怎么开？那这样子它的 kernel stack 的话，我以为是每个 process 都会就是 allocate 一小部分给 kernel stack，所以它其实它的意思是说，在 DRAM 里面的某一块物理基体位置都是给 kernel stack 用的吗？
对，就是它会有一块是给 kernel 放东西的，其中就会包含 kernel stack。
哦，所以说那一块基体位置其实是给任何一个就是正在运行的 process 之后当 kernel stack 使用的。是可以这样理解的吗？因为都说这一块可以映射到同一个。对，哦，好。
但那个很大。
OK，
那会有一句。
OK，好。那还有那个，想要问那个kernel thread 这边，就是有点不太懂，就是最后这两句话的意思。这 kernel thread 它一样是像一个 process 一样吗？只是它会变成没有切一部分给 user space 这样。
对。就是它没有 user space 那一块。
那这样为什么会说它没有 address space 的原因是？
这个是没有 user address space。
没有 user address space。
对，它还是有 kernel 的那一块。
所以这里说operates only in kernel thread 就是代表 CPU mode 要是 kernel mode 的时候，它可以跑这个 kernel thread。
没错。
OK， 好，谢谢。
交出来就是那个我有选修那个大学过作业系统，但是忘记退这门课。
没问题。
那请问一下，可以帮朋友代签吗？因为他今天不在线。
可以
，OK 吗？
可以。
签真表是没有的。
好，
接受。
我有一个问题，就是说我 P1 fork 出 P2、P3的话，那我 P2 改的话，因为我 P1、P2原本共享一个记忆体嘛，我 P2 改的话，P2 会有一个新的那个 page frame，那它是那个新的是全部复制过来，然后新的还是只有我改那一段是新的出？
哦，这是好问题，就是在我们现在系统里面一定要改一个 page，就它也是搬一个 page。所以基本上，它只要改配里面不管哪个地方，它就会去把它搬到，它就会allocate一个新的 page，然后把它写过去。
所以它不是改一整份，
它是改以 page 单位去改。
好，那这样的话，那它改了之后还是可以存取原本跟 P1 共享的，对吧？因为它只改一个page的话，
不行。它改完之后，就是它有点像这样的，就是它改完之后，它就会有一个自己的一个 page。然后呢，当然你可以说它没有被改的部分，其实它跟 P1 是一模一样的。只是这时候他们就不是共享了。
所以它还是会贴全部过来，然后只是改一个 page。
对。
那所以如果我今天我 P1 fork 出 P2、P3，那我改 P1 的话，所以 P1 也不能存当初跟 P2、P3有共享那个。
没错 ，P1 就会自己有一个就是新的 page。
就是它做自立门户的感觉。
对。
然后 P2、P3 也不能存 P1 的新。
对，谢谢。
想问一下，就process 的话要用 fork，然后会用 Fabian 来继承。那如果在 create thread 会用这种法？OK， 也是用这种。
但其实 create 对的问题比较不大，因为对于这个状况来讲的话，其实 page frame 这一些其实需要改的东西比较多，因为 page frame 要占空间。
所以
它本来就
那个本来就是
对啊，它本来就共享的，对吧？对，所以通常大家在 copy on 都是讲是 process，但你要说对了可不可以做到，也可以做到。对。
那另外想问，就是因为像 假如一个 user process 它要切 kernel，会不是有 kernel 或 user ROM 那像他在跑 user threads 或是 kernel threads 的时候，他会不会有这种问题？还是他怎么判断说，他们怎么判断方法说现在是要跑哪一种 thread，或者是还是他们全部都同时进行？
什么意思？我
就不太知道他什么时候跑 kernel。
哦，对，就像是你可以想象，它就是类似它排程到它的时候，CPU 就会跑 kernel，所以它跟大家是一起排程的。就是今天我 kernel 队换到它跑的时候，那它就会这个 CPU 就会跑这个 kernel 队。
那他需要像 process 这样切换什么 mode，还是就是还是他就只是
它要在 kernel mode 才可以跑 kernel 队。所以如果今天，
change 到那个
但是
mode
但是问题是，你在跑 scheduling 的时候，它本来就在 kernel mode，所以它不用换。
哦，他只是跑他对应要的，
没错
对，
没错。
哦，OK，
好
对啊，
这样。All right, so let's come back. There are several questions, so let me answer one by one. So one moment. Okay, so there's a question is about like, if I understand correctly, she's asking about just like, because each process has their own process descriptor. So is there any integrity issue there? So actually you can think about process is a concept about to try to become high isolation. So in most cases, process is a safer way because they have their own isolated resource there. So for this question, I would say usually process has great integrity. Sorry. So the other question is about IO things. So I would say like IO thing will be introduced later, several few weeks later. So I think for the IO things, yeah, let's wait for the interrupt and then the IO service here. And okay, coming back to the copy on write. So the question is, will the kernel record about, for example, for this patch frame, how many process share with this patch frame? Yes. So actually there is a counter here to keep track of how many process share the this patch frame. Okay. So if the counter doesn't count to 1, actually when there is a write operation and then there will be a new patch frame will be allocated. Okay. But if this frame, if this frame is only belonging to one process, what I mean is if the counter becomes 1, then we don't need to do the copy. Okay, you can just directly modify this patch frame. Okay, so if this is the last frame and there is no one to share with you, then you can just directly modify it. But if there's not, for example, if the counter becomes 2 or even more than 2, then we will copy out the new patch and then to modify the new patch. Okay, so this is the concept of the copy on write. And I think it's on the same patch is here. So people are curious about why here we've write 4 label here. So long story short is because current Intel use 4 label patch table. So usually there is not only one patch table here, there are a lot of label here. So you can think about there are several page tables here in current Linux, and we will go through this during the memory management topic. And there's another question is about when will the process set their state to the text uninterruptible. So in most cases, the uninterruptible state will be set in the, one moment here. So for the text uninterruptible state will be set during the fork. So when we are going to fork out a process, we will use this state because we don't want any other signals to interrupt this or kind of procedure, because this is the initialization stage. So this is a super spatial state, I would say, because in most cases, if there is an IO service like this kind of things, people are using this interruptible state. Okay. How many kernels are running on a 4-core processors? Is it 4? Okay, so I think I should put it like this. So as you know, like kernel is just like a bunch of like kernel functions there. So you can think about it is also possible. I mean, if you have, a multi-core systems and each core run one like scheduler and the other run other like memory manager, it is also possible to do like these kind of things. Okay. So, yep, that is for most questions. Let's come back to the scheduler part. Okay. Okay, so I think we stop here, just like we are wondering how to decide the time slice and then how to decide which process should be run next. So the time slice, definition of the time slice is the time between when a process starts to run and the process being interrupted or like being preempted. So this is called time slice. Okay. So process priority. Actually, each process has their own priority, right? So usually in Linux, we use a thing called nice value to represent what is a priority for each process. So a larger value represents being nicer to others. So you can think about larger value means lower priority, okay? Because it being nicer to others, so the process will give up more kind of resource to other, okay? So lower priority usually means normal process, okay? So why I say normal process for low priority, because there are some other process called real-time process, like kernel process, and then those kind of process actually they have higher priority. Okay, we'll talk about it later. Okay, so real-time means like we want to make sure there is one process that can finish before one like timing. So this is called real-time. So there is hard real-time and soft real-time, and you can think about just like this process should have their kind of should have their criteria to say, I want to finish my process, for example, in 1 second. So if we don't want to fail this 1 second assumptions, then they usually should have higher priority so they can preempt lower priority process. Okay. Okay. So on the right hand side it is a really kernel version is Linux 2.6, but I think this is quite representative for this example. So you can see like there are nice value from 19 to -20. So as I say, larger value means nicer to others. Because you are nicer to others, so you don't want to occupy CPU for too much of time. So nicer to others, it means like you have higher like 19, for example, then the time slot you can get is only 5 milliseconds. So 5 milliseconds means like for each 5 milliseconds, you need to switch out to other process. You need to release the CPU to other process. So you cannot run more than 5 milliseconds. Okay. So for the higher priority process, just like -20. So -20 is the smaller value. So usually this will be the highest priority process. So -20, it means you can get 800 milliseconds for time slice. So 800 milliseconds means like it can run for a super long time. It is around like 160 times longer than 5 milliseconds. Okay, so you can think about longer time slice means the process will occupy CPU and the memory for a longer time. So you usually will run faster to finish their process. Okay. Okay, so actually on the right-hand side, we call this code static mapping. So static mapping is because, hey, if we say this process, the nice value of this process -20, then it will directly get 800 milliseconds. So if one day the system administrative set the process to 19, the lowest priority, then its time slice will simultaneously change to only 5 milliseconds. So there is a one-to-one mapping between the nice value and the time slice for this static mapping. So later you will see, actually there is another thing called dynamic mapping. Just like the time slice will not be decided at the moment you get a nice value. I mean, there are some criteria there, so the nice value, sorry, so the time slice will be fluctuated. Okay. So for this static mapping, actually there are two challenges. The first challenge is triggers context switch frequently if all processes are low priority, right? Because the nice value of these kind of things, usually they are given by the system administrative. So usually for those high priority, I would say larger than 0, usually normal process will not get this nice value. Because those nice value larger than 0, they are given to the, for example, kernel process or like real-time process. So in most cases, you will see your normal process will have a nice value lower than 0. Okay, so probably maybe it's something between here. So usually you will say maybe most process you can get nice value like 9 or 10, for example. So here comes the case. If all the process only get 10, it means each process will be rescheduled in 5 milliseconds. Okay, but this is super time. This is super high overhead because for every 5 seconds, CPU should run a process context switch. You need to switch in all the process and switch all the current process. Okay, so this is the first issue. Just like CPU needs to do frequent process context switch if most of the process they are in a low priority. And the second challenge is about the time slice difference is huge for process with higher nice value, which means low priority process. So what does it mean? Let's do some calculation here. So if you are the high priority process, you'll get, for example, nice value -20 and -19, right? So let's focus on -20 and -19. So actually the time slice is 780 milliseconds and 800. So it means the difference is only 20 milliseconds for the high priority process. It doesn't really feel too much of difference because, I mean, if you can get 800 milliseconds, even you have, I mean, even you only get 780, actually there's only kind of, I would say like 5% reduction here. So it doesn't really matter that much, right? But the thing is, if you are a low priority process, you only get nice value 19 or 18, it matters a lot because 19 can only get 5 milliseconds, but 18 you can get 10 milliseconds. So when you compare 5 milliseconds to 10 milliseconds, actually it is twice more times, right? So it matters a lot. So it will lead to the resource unbalance issue. I mean, for those low priority process, their time slice has a huge gap there. Just like for lower priority, you will have like twice of the difference time. But for high priority process, it doesn't really matter that much. No matter -16 to -20, actually, it doesn't really have too much of difference there. So how to deal with these two challenges? There are kind of Linux kernel scheduling they are thinking about. So we will introduce 3, Linux kernel scheduling. So one of them called CFS is from 2.6. It's quite familiar. It's quite famous in the past years, and CFS can solve most of the issues here. Okay, but I'll introduce from the historical one by one. Okay, so after finishing time slice, there are also several characteristics related to the process scheduling. The first is I/O bound or compute bound. So I/O bounds means it spends much of time submitting and waiting on I/O request. So for example, keyboard, network, storage, they are most of them they are I/O bounds. So like graphical user interface, the GUI things. So GUI things is when you type something, then on a keyboard, then on your screen, you will see something will pop up, right? So for a keyboard, maybe you type 1 to 10, then the monitor will show 1 to 10. This is the GUI things. But actually GUI is usually I/O bound because it doesn't really do too much of computation. It only shows the things you type to the keyboard, okay? So the policy for usually for I/O bound is to run more frequently, interactively, a shorter time slice, right? Because what we need is interactive. Because when you type the keyboard, you don't want to wait for like 1 second or even 10 seconds for the for things to show on the monitor, right? But it doesn't really need too much of time slice because it doesn't really use too much of CPU resource here. For time slice, it can be super short because we only need to fetch the data in the buffer and then show them on the monitor, and we are done there. Okay, so this is for I/O bound. So you have I/O bound, it means like there is another opposite is processor bound. So processor bound means to spend much of time executing code. So usually like SSH key generation. So like if we are going to generate a SSH hash, then it needs to compute a lot of things, or maybe like MATLAB. So you are going to do some mathematical things, okay? So for this kind of process, actually it runs less frequently. So what I mean less frequently is compared with this kind of keyboard things. Because keyboard you type very frequent, right? But compared with the SS key gen, usually you will not gen a key so frequent, right? So this is just like the comparison there. And usually because you are processor bound, so you need longer time slice, right? Because you want to generate a SSH like SHA-1 hash there, so you need CPU to run for a longer time. Okay, so here just a decision to let you know like not really like all process need a lot of CPU resource. There are some process actually they need more about interactiveness. They need more process to release the CPU resource out to them, and maybe they just need 1 millisecond or even less to finish their task. Okay. Okay, so the last thing to let you know is actually when we are going to design, actually there's not only the scheduler thing, actually in the entire kernel or even in other systems, overhead is quite important. Just like, for example, when we are going to find the next process, there are several tons of data structure you can do these kind of things, right? There are queue, there are tree, there are bitmap. So different data structure, they have different complexity there, and they have their pros and cons. So how to pick a right data structure for this scenario is a critical thing. Okay, so there is one interesting thing is, when we are going to pick the data structure, there is also how to implement the data structure, right? So complexity is one thing, but for example, if there is a global run queue, or actually there is a per processor run queue, actually it also matters a lot. Because, for example, if there are several processors there, then for all the processors, they share the same global run queue. So for one processor, they are going to get the maybe process out from the run queue, it needs to lock the queue. So other processor will not access this global run queue. So it will take a lot of time for other processors to use this global run queue, but it is easy to implement, right? People usually like the global things, because global just like you can assign a global parameters and you don't need to take too much of time to rewrite your program, okay? So this is about the global things. All right, so those are all about the criteria. So let's now give you some example to let you feel like how Linux design their own scheduler. So let's start from the very beginning, kernel version 2.4, and this is a single one. People call them big O-N. Okay, so it is quite simple. All processors share a global run queue. or you can think about to share a ready queue. And it's sort of processed by their priority. So it is quite easy, right? When there is a process add into the run queue, and because maybe they will get a nice value and they will get a time slice, so we can do a sorting, and we will always pick a high priority process out from the global run queue. Okay. And there are several kind of bad things for this design. First of all, system should lock the run queue when a process run out of its time slice. Okay, so when one process is finished and it is going to pop out from this run queue, actually, system should lock this run queue. And because this is a global run queue, so when the run queue is locked, then no other processor can access this run queue. So all the other processes, if they're going to run the scheduling, they will be busy waiting here to wait for this run queue to be released. Okay, so there is another thing is process should be inserted to an expire queue in order. So it means like if we are going to like insert the process, no matter in the run queue or in the expire queue, we need to do, for example, the sorting things. So it takes a lot of time if there are a ton of process. I mean, if there are only 5 processes, it doesn't really matter. But I mean, if there are like thousands or even 10 of thousands of processes there, each time when you are going to do the sorting, it takes a lot of time, right? So this will be the case. If there are too many processes and you use this ON, then usually probably you'll get ON of time here, okay? Because you need to do a sorting, okay? And maybe more. So we need a faster one. So in the kernel version 2.4, they introduced a faster one called O1. So O1, just like their name, they're going to let the scheduler to run like O1 of time, super fast, right? So how to implement these O1 things? Actually, there are 2 data structures here. So first of all, there is an active bit array. Okay, so what do I mean for active bit array? So actually in Linux, you can think about there's nice value there, right? So if, for example, there are 140 priority here, so you can think about maybe there are 140 nice value, but actually you only see 40 here. I will let you know there's another 100 later. So in summary, if we have 140 level of priority, so each priority will get 1 bit, okay? So each bit will be set if the corresponding process is added to the run queue, okay? So for example, you can think about this is the, for example, highest priority, and this is the second highest priority. So if there is a process, it is second highest priority, and it is added into the run queue, it's added into the ready queue. So once there is a process inside, we will mark here, okay? So the O1 runs like it checks active array to get the target priority value, okay? So after getting this target, I would say bits, so this is second bit, right? So actually they will have another data structure called active array. So because there are 140 bits here, so actually there are 140 active arrays here. So this is Q0. Q0 is for the highest priority, and Q1 is for the second highest priority, right? So when there is a process, or like people call it text here, when there is a process added into a ready queue, we will use a chaining to chain them in the queue. So for the queue, in the same queue, they will be in the same priority, okay? So in this case, if we are going to get the next to be scheduled process, what we are going to do is to check from the leftmost, because this is highest priority. So there is no one in the highest priority, right? Because there is not set it. And if you are going to check it, to double check it, you can just check the active array. Actually, there is no process in the topmost Q0, okay? It means there is no highest priority process they are going to be scheduled. Okay, so we will check for the second one. Okay, so second one in the bit array, this bit is set. right? So because this bit is set, it means in the active array part, the corresponding queue, there are some process inside. I mean, there may be one, and maybe there are more than one. They are all possible. So we use a FIFO to get the process out from this active array. So using the FIFO, we will get the text one out, and then we will say, hey, let me schedule the text one. Okay, so this is just a way to implement O1. Okay, so coming back to the question, why this is called O1? Why it is possible to do it O1? I mean, we still need to check for the bit array, right? So the reason is, here are some tricky things. Actually, for this bit arrays, it cannot be any bit arrays. It should be tailored for a CPU. So in a CPU, there are some spatial instructions here. So for example, the reason for this rule is 32 bits is because for each instruction for CPU, it can read for these 32 bits together at the same time to the CPU. Okay, so after reading the 32 bits into the CPU, there is instruction. There is an instruction in CPU can fastly get the leftmost bit out. Okay, so with this CPU instruction, we can quickly know which bit is set. Okay, we only can know where is the first bit is set in this 32 bits array, or like in this 32 bits bitmap. Okay, so it relies on CPU's kind of accelerations to quickly get out where is the first index that is set. Okay. Okay, so we only talk about the insert part. So actually there is, when the process use up the time slice, right? So we need to recalculate the priority and enqueue to the expired bit array. Okay, so you can think about, actually, here is the bit active bit array. So we need the same one, but therefore expire. So expire means like the process use up all the time slice, right? So, but even the use of their time slice, they still are not finished. So they need to put to other place. So other place is, it will have the same one. It will have the duplicate one, but the name will be expire bit array. So because we have the expire bit array, so it means like we also have the expire array for this one. So you can think about this pair of the data structure, they have two. Okay. So one for active one and the other pair for expire one. Okay. So for this design, why we need two? Because when no bit is set in the active bit array, we just directly switch active and expire bit arrays. So we are finished. Okay, so we will schedule all these kind of process out, and then when this active array, there is no process in the active array, and for the left-hand side, the active bit array part, if no bit is set, then we will switch this bit array, we will switch this active set to say, hey, that you become expire one. So the expire one will become the active at that time. Okay. So we can then resume the scheduling, and then we can use the original expire bit array to become the active, and we can do the following scheduling. So in this case, actually we only need 4 data structures: one active bit array, one expire bit array, and a corresponding active array and expire array. Okay. Then we can finish this O1 scheduling thing. Okay. So question? Oh, okay. So the reason for there are 4, because you can think about this bit array is only for the active, but you also need another one for the expired. So we will have one bit array for the active and the other bit array for expired, and then also for the active array. So those active array here is only for active. So we will have another set, another Q0 to Q139 for expire one. So this is the reason why I said we need 4. Yep. Okay. The reason is, okay, one moment. Okay, the reason is in Linux, here, from 19 to minus 20 here, there are 40, right? 40, they are for normal process. And there are a set of 0 to 99. I mean, nice value, they are for real-time process. So in total, they will have 140. So there are 140 priority for normal process plus real-time process. Okay, but in this table, I only show you the normal process part. So actually, this 140, it depends on how many priority level they are. I mean, if you change the kernel code to assume there are, for example, 200 priority level, then this 140 bits should be changed to 200 bits, like this. So it is customizable. Okay. Okay. So okay. So what is the drawback for this O1? Actually, there's a one really huge drawback is it has low interactive performance, right? Because you always start from checking on the first rule, and then the second rule and the third rule. And the first rule only has contained the highest priority process, higher priority process. Okay, so when it comes to the later, this will be the lowest priority process. So for example, if there are always new process being created, and if the new process has higher priority than the last one, then the last one will never be scheduled. Okay. So this is called low interactive performance because the last one will never get the chance to be executed. Okay, so it is not really fair. I mean, it is good for high priority process, but if you are a low priority process, probably you will get the CPU resource. You need to wait for a super long time. So I'm going to introduce another one. Is the start to use begins kernel version 2.6. It is called completely fair scheduler. Actually, this completely fair scheduler, you can see like O1 is before 2.4, O1 is 2.5, and CFS is 2.6. So they are in a similar times. Not really similar times, but I mean, they're close to each other. So CFS used for a super long time. If I remember correctly, the latest scheduler is after kernel version 5, something like that. So CFS used for a super long time. It's for like several 10 years here. Okay, so CFS, the goal for CFS is to make the scheduler more interactive and more fair than O1. Okay, so here are two concepts. The first is, instead of statically mapping time slice, each process would receive 1/n of the processor's time, right? So actually, let's say about like static mapping means like no matter how many processes they are, if they have high priority, they can get a lot of time slots, right? But if there are too many processes, it means lower priority has literally no chance to run the process. So a way to solve this problem is, why not just say, for example, if there are 10 processes and these 10 processes need to be run, for example, each second. So for each seconds, the 10 process just share this 10 seconds. Sorry, to share this 1 second. So you can say maybe high priority process, they can get like half of the second, but the rest of them, they still need to be scheduled in for the rest of the half seconds. So every process can be run in this 1 second, and then we will start for the next second. Okay, so it means like we can make sure all the process can be run in this predefined time slice. Okay, so the other thing is to schedule process for infinitely small durations. So this is also to deal with the static mapping, because static mapping, like if there's no IO, in most cases, we will reschedule them when they finish their time slice, right? But the same thing, high priority process get too many time slice. They're too long. So if, for example, we only have, for this 10 process, you can only run it inside 1 second, then for all the process, they will be rescheduled in the inside of 1 second. Okay, we'll have more example for this later. So we need to first define one thing is called virtual runtime. So virtual runtime is the real system runtime plus priority. Okay. So we're going to keep the virtual runtime of all running process the same. So here is a calculation here. So virtual runtime equals the delta execution times nice wait over nice k wait. So it is quite complex. I mean, it is just like delta execution is the period to enter scheduler. So as I say, if there are 10 processes, you can say I want to reschedule the scheduler each 1 second. So this is called the delta execution. So we have n process, and we are going to reschedule them in how long. And in Linux, this is a constant. Usually it's 0.75 milliseconds or 6 milliseconds. So for each 6 milliseconds, no matter how many processes you are running now in the systems, they need to be rescheduled again. Okay. So nice wait over nice k wait, it is just for each process they have their nice value, right? And nice k wait means we are going to sum up all k running process. Okay, so this is about the fairness, because just like, for example, nice wait maybe for the first process is 1, and then for the overall k process maybe is 10. So we can get 1/10 of the delta execution for running. This is for the first process, and then maybe for the second process, this nice value get a little bit higher, like 2. Then you can get a little bit more for the time slice. Okay, so but the problem comes here, just like actually nice wait here, it is possible to get the floating point, right? Because this is smaller and this is larger. So here is a floating point. And then in Linux, they are going to support these things because there are some cases like some CPU doesn't have the floating point unit. So if you're going to trace a Linux code, you will not find this formula. What you will see is here, the practical one. So you will see like they are going to times the 2 to 32, and then they will ship the 32 things. The reason is if they times the 2 to 32, and then for this calculation, they can try to avoid to touch the floating point. Okay, and then there are some tricky way to let them ship back. So this is just a practical to let you know, if you trace a Linux code, you will not really see this theory one. You only see the practical one. And this is the reason because Linux want to support those CPU doesn't have the floating point unit. Because CPU, if there's no floating point unit, then you will take a lot of time, usually 10 times or even more times for running these floating point operations. Okay, but I mean, this is not important. I mean, in the exam, I will not say, please explain why like these kind of things. Okay, so don't worry. So after doing the calculation, so each process will get their virtual runtime, right? So virtual runtime, the smaller one means like it most need of CPU, and a larger one means least need of CPU, like this. So they use a red black tree to maintain all the virtual runtime for each process. So the reason to use red black tree is because it is a balanced tree, so it can control when they are going to find a process, which process should be rescheduled next. Actually, they can directly get the leftmost node in log n time. So this is the reason why they are using red black tree. Okay. Okay, so let's focus on the theory formula. So we say we are going to time the nice wait over nice k wait, right? And the reason for this one is to make the scheduler becomes more fair. Because for this part, it means if all the process is going to share this delta dash execution time, for example, 6 milliseconds, then how much can each process get? So it depends on your priority. If you get higher priority, maybe you can get half of them. For example, you can get 3 milliseconds. Okay, but we can make sure in these 6 milliseconds, all the process can at least touch the CPU once. Okay. But here comes the problem. How to decide the wait? So remember, we talked about if we use static mapping, the question is for the low priority one. Let me remind this one. So if we use static mapping here, it means given you a nice value, we can quickly get the time slice here. And then for this case, there is a resource unbalance because for low priority process, the time slice is so huge. I mean, the gap is huge. There's 5 milliseconds and there's 10 milliseconds, right? It is not that fair. So for CFS, they're trying to solve this problem. So what they're using is called a 10% effect. So if you open up your Linux source code, you will see something like these kind of things. This is just directly screenshot by the Linux kernel 4.4 things. So let me just give you some hints about why there is a thing called 10% effect. So there is a priority. So 0 to 40, right? So there is minus 20 to 19. So here are all nice value from 19 to minus 20. Okay, so this one is for the process getting nice value 19. It can get, for example, 15 milliseconds for running. Okay, and then here is like at 761. Okay, so not really is millisecond because actually this is kind of for wait. So, but I'm going to analog to the static mapping. So you can image like this is just like very close to the time. Okay, but I'm going to emphasize this is not a time because the virtual runtime show time the delta execution. It will become time, and here there are only waits. Okay, so you can see like for the 15 and 18, actually the difference between them there is only 10%. Okay, so if you, as I show, like for the static mapping in the traditional version, there will be 2 times larger. Okay, so not only the low priority process, also the high priority process. If you do the calculation to do the calculate for the topmost 2 priority here, actually the difference is also 10%. Okay, so for high priority process and low priority process, they look fair for getting the weight value. Okay. And maybe you will have a question about, so how to get this kind of weight value? Actually, there's a lot of calculation. I will not show here, but if you are going to get the value out, actually there is a quick mapping here. So the weight, how to calculate the weight is like this, just like there are several nice value here from 19 to minus 20, and here is a priority, and you can get the weight value from given a nice value, and here is a calculation way to get the weights here. Okay. Okay, so I think that is for the CFS. So let's call it a day. So see you guys next week for the real-time scheduling part. Thank you.
因为那个 delta execute time 是全部的process 分嘛。
是全部的，
对，那刚才
全部被排成的 process。
对，可是像刚才那个 static 的 mapping 的方式，我们可以看到说那个 nice 的最高的那个人，他也有5 microsecond。
还有5，对。
可是以现在这个 CFS 的 case，他说我有可能一个 delta execution time 只有6 microsecond。
对啊。
那这样除下去，不是每个人都非常少？
对啊。这就是为了确保不要有人独占 CPU 太久的时间，因为它有个假设是它要分的越频繁越好。对啊，就是你这个是可以设，你也可以设什么0.75，它更短。
只是那个 context switch 的比例就会 overhead 的比例就高。
但是因为 context switch 的时间是 microsecond 等级，所以跟 millisecond 还是差蛮多的。对，这也是为什么他们会特别调到什么 millisecond 这个来。
0.75感觉也跨下去 microsecond。
对啊。但是我觉得这就看你的 kernel 要怎么去做最佳化，因为如果你 kernel 是为了某些状况设定的话，它还是不希望有某些 process 真的花很多时间在它身上。好，对，对，谢谢。
我在懂，还是没懂刚刚问的问题，就是它是 active 加一个 expire，它为什么还要各在一个？
因为是这样的，它各一个是这个一个资料接收，这个也是一个。所以它是4个，对吧？因为这 feed array 它就是 array。
那我想问，就是它不同单词对它有这种。
我那只是想让大家知道说，其实就是 这边算是一个资料结构，是 bit array。
哦，
那这边算是另外一种资料结构，是多层的 list，但是它 active 需要2个，对吧
对，
？expire 也需要2个，
哦 big list，
对，expire 也需要一个
big
这个，
list，然后这个是 big list。
对，所以我 expire 也是需要同样一组。
那这里 big array 意思是说，如果我这个 priority
有人，
那就是一。
那就是对，它只有1或0，
哦，OK，
有或没有的意思。
对，好。然后我想问，那个什么 FIF 是什么意思？
哦，就是 first in first out，先来就先拿掉。对，
那这个东西，所以它这个是必须细节，对，不会去。
对，我们好的东西是这样子啊，
这个嘞
就是只要知道后面，这个基本上就是只是示意一下跟大家说，它会长这样。哦，因为你现在如果有100个 process 好了，每个 process 都有个 virtual runtime，那你怎么知道最低的是谁？
哦，
因为我因为
排序，
对啊
排序
对啊
对，
但实际上排序怎么去实做，那就是这样去实做。
哦，
对，
为什么它要有2个，一个是 expire，一个是 active 的，之后2个在换？
因为 active 用完之后，它可能还没跑完的 process，那个因为它 active 可能每个人都只会拿到一段时间而已。
对，它都会换到
对啊
expire。
那它就放 expire。那所有的 active 跑完之后呢，它只要把资料结构 switch，它就可以了。它就可以把 expire 变成 active，active 再变 expire，它就可以再重新再做一次一模一样的事情。
为什么不要直接把我想一下，因为 bit 是只代表是只代表说有没有这种 priority 的 process 在系统里，
对，
所以它没有办法代表说它是已经
对排成
在
完还是
对，所以它需要2个去做这种表示。OK，
没错。
好，谢谢。
那个什么，就是优先级里面不是有很多 task 吗？那就是照时间先后顺序去排的嘛。如果是同一个 priority，要执行的哪一个先执行，就是时间先的。这个当然是 first in first out。
当然再提
说，如果有相同 priority 的 process，如果好几个，比如说 task
对 first in first out，
对，
照顺序。对，
所以这个 task 一就是 task 看这个就是看谁先进，
谁先来就先。对，没错。因为下堂课的人要进来，所以线上的问题我就下次再做图面回答。感谢。好，我是
这个 bitmap 当然是说要整个 active array 跑完，它才会 switch 掉。那可是假设说我今天是一个很 high priority 的 process，它被碰到 expire array，
对，
但是它要等它这个全部跑完，
对，
它才会在所以这样子，它假设才稍微用完，它还得等很久。
对，
OK，
对，
可是它是 high priority，它没有办法在。
它其实这边没有讲，但是它如果要的话，它还是可以去 interrupt 的。因为这边讲的是没有 interrupt 的状况。对，但是那又是另外一个状况。
好，了解，谢谢老师。
对，谢谢。
可以。